If you find maths hard, you're in good company, because some of the greatest mathematicians of the past struggled with the maths that you're supposed to know. Until a few hundred years ago, maths, like reading and writing, was the preserve of the ruling classes. Priests and scribes, merchants and scholars. But now we're all expected to use it. So we're here at the Science Museum stores in London to see where some of our maths came from. Think of a number, any number. But where did they come from and what do they mean? Our number system uses just 10 digits, 1 to 9 and 0. And depending where a digit is in a number, it has a different value. So this is 2. This 2 means 2 tens. And this 2 means 2 hundreds, and so on. Our hundreds, tens and units. And if there aren't any digits in a place, we put a 0. But it wasn't always like that. In earliest times, numbers were used to count things, bushels of wheat, sheep, and they were written as simple tally marks. But it's difficult to count a lot of tally marks. So the next idea was to bundle them into groups and count the groups. Around 5,000 years ago, the ancient Egyptians used this grouping idea in their number system. They used a series of hieroglyphic pictures, and each picture was worth 10 times more than the one before it. Number 1 was a straight line, 10 straight lines made 1 heel bone, 10 heel bones made 1 coil of rope, and so on, up to the god Heh, who was worth 1 million. The Egyptians made any number by using the right number of symbols. So 2084 would be 2 water lilies, 8 heel bones and 4 straight lines. At the same time, the Babylonians, who lived where Iraq is now, had a different approach. They used just 2 different kinds of arrow strokes to make all their numbers. Here's a Babylonian clay tablet at the Science Museum collection with a mathematical problem about right-angled triangles. It's written on clay because paper hadn't been invented then. And these marks were pressed into wet clay using a wedge-shaped stylus and then allowed to dry. The Babylonians counted in 60s, so to write their numbers, they'd start with lots of marks for 1 until they reached 9. Then turn the stylus on its side to make a 10. Then they'd use combinations of 1s and 10s to make numbers up to 59. The Babylonians' breakthrough was what they did next. To make 60, they didn't use a new symbol like the Egyptians did, but moved along one space and used the same mark as they'd used for 1. Then on they went, using the same set of symbols all over again and again. If there was a position with no number in it, the Babylonians left a gap, which could be a bit confusing. So they eventually hit on the idea of putting a little mark in the gap to show there's nothing there, which is the first sign of something like our 0. Here's our number 2084 in Babylonian script, which they'd write as 34 60s and 44 units. These Babylonian numbers are the first sign of a number system where the same symbols can have a different value depending where in the number they are. A place value. In China in the 4th century BC, the ancient Chinese used rods arranged on a counting board. They made different combinations of rods for the numbers 1 to 9. And once they got to 10, they moved along one place and used the same combinations of rods again, turned sideways to avoid confusion, and so on, with each position worth 10 times more than the one before it. So the Chinese number system was based on 10, like ours. Here's our 2084 in Chinese numbers, with a space where we put a 0. By about 200 AD, the Chinese had developed the abacus to do calculations more quickly, with beads on wires to make the numbers. This abacus in the Science Museum has 5 single beads and 1 bead worth 5 in each row, with each row worth 10 times more than the one before it. So this is 2084. But what was happening in Europe at this time? The The Roman Empire covered most parts of Europe and parts of Africa and Asia from around 30 BC to 450 AD. The Romans used 7 capital letters for their numbers, which were easy to carve into stone or scratch in a wax tablet. Paper still hadn't been invented yet. These letters went up in multiples of 5 or 10, and the Romans made all their numbers from them. So here's our 2084. This wasn't a place value system like the Chinese or Babylonians, because it used different symbols for each value, more like the ancient Egyptians. The Romans had no zero, big numbers were really awkward, and multiplication and division was very difficult. Despite all these drawbacks, Roman numbers were still used in Europe by church and state officials for centuries after the Roman Empire had collapsed. But the number system we use now is nothing like the Roman system. So where did it come from? It was in India from around the 4th century AD that written numbers started to appear that we'd recognise. They used different symbols for the numbers 1 to 9 and moved them along one place for each multiple of 10. And instead of leaving a gap where there were no numbers, the Hindu mathematicians used a little dot or a circle, the first sign of a proper zero. News of the new numbers soon spread to Europe. Early in the 13th century, the famous Italian mathematician Fibonacci wrote about them in his book of calculations. The 9 digits of the Hindus, the knowledge of the art of which very much appealed to me. And he explained how, with just these 9 figures and the sign 0, any number may be written. But despite Fibonacci's enthusiasm for the new numbers, the authorities in Europe preferred to stick with the old Roman numbers they'd been using for 1,000 years before. This held up mathematical progress in Europe for years, and it wasn't until the 16th century that the Hindu Arabic numbers we use today finally become established. In his book, Fibonacci also wrote about how to work with the new Hindu numbers. This shows how to multiply large numbers using the Hindu grid system. And this is how it works. To multiply 56 by 28, you draw up the grid and fill it out by multiplying each pair of digits in turn, like this. And then add the results in each diagonal. So our answer is 1568. By the end of the 16th century, this was a standard method of doing multiplication. In the early 17th century, the famous Scottish mathematician John Napier invented a simple calculator to help with this grid multiplication. They were called Napier's bones, and here's a set in the Science Museum's collection. You arrange the bones to make the number you want to multiply, say 2084. And to multiply by, say, 4, you'd read the results across the 4th row, adding the digits in each diagonal to get 8336. From then on, more devices were produced to help do calculations quickly, such as mathematical tables and slide rules, and mechanical calculating machines that use gears and cogs to add, subtract, multiply and divide. Multiplication is repeated addition. So to multiply 56 by 28, you turn the handle 8 times for the units, and then move the carriage along and turn it twice with the tens. By the 20th century, electronic calculators made working with numbers even easier. Now we can get an instant answer to the most complicated problem, but it will only be the right answer if we put in the right numbers and press the right buttons. But whilst modern electronic calculators make working with numbers easy, they also make it easy to forget how our number system works and how wonderful it is. If you find negative numbers difficult to understand, you're in good company. As recently as 1759, a famous British mathematician wrote that negative numbers darken the whole doctrines of the equations and make dark of the things which are, in their nature, excessively obvious and simple. And he went on to conclude that negative numbers were nonsensical. You can understand him saying that because, after all, numbers were used to count real things, and mathematics was about calculating real quantities. So how can there be a quantity that's less than nothing? It's not surprising negative numbers posed a problem. In ancient times, the Greeks had no negative numbers because their maths was based on geometry, in which numbers represented real lengths, areas or volumes. Around 250 AD, the Greek mathematician Diophantus wrote a famous book about equations and looked at what we'd write as 4x plus 20 equals 4. Now, the Greeks didn't write equations like we do, but would say something like, how many things, when multiplied by 4 and added to 20, is equal to 4? But Diophantus pointed out that 4 is smaller than 20, so that's absurd. And so it would be to the Greeks. Our solution of x equals negative 4 would be completely meaningless. In India, in the 7th century, the famous Hindu mathematician Brahmagupta explained negative quantities in terms of debts, and he came up with some rules for doing arithmetic with them. A fortune subtracted from 0 is a debt. A debt subtracted from 0 is a fortune. And a debt times a debt gives a fortune. We'd go along with that now, but mathematicians remained very suspicious of negative numbers for centuries to come. Even in 16th century Europe, resistance to negative numbers continued because most maths was still based on practical activities, such as science, commerce or warfare, in which negative numbers had no meaning. Mathematicians still called them absurd and rejected negative solutions of equations as fictitious or false roots. It wasn't until the 17th century that an English mathematician, John Wallis, came up with a novel idea of explaining negative numbers by showing where they come on a number line. In his treatise on algebra, Wallis gives the example of a man having advanced 5 yards, thence retreat 8 yards, and it be then asked, how much is he now advanced? I say because positive 5 subtract positive 8 equals negative 3, that he is advanced by 3 yards less than nothing, which is exactly how we think of numbers on a number line today. And now, negative numbers are on the school syllabus, so you too can relive, but hopefully avoid, the difficulties that plagued the famous mathematicians of the past. For as long as people have engaged in trade or built things, they needed to measure things, and much early mathematics was based on calculations that used these measures and recorded the result. Early units of measurements were based on parts of the human body, such as inches, spans, cubits, feet and yards. Others were based on human activities, such as bushels, stones, acres, pints and miles. But these human measures varied from person to person, and those based on traditional activities varied from place to place. Measures needed to be standardised across the country, and accurate versions kept in a safe place for reference. Here in the Science Museum collection is a set of 500-year-old standard measuring jugs from Tudor times. That's a gill and that's a pint. This is a standard yard. And this is a standard £1 weight. As trade between different countries increased, universal standards of measurement were needed. From the 17th century onwards, Britain had an empire that stretched around the world, so those countries used the British imperial measures of feet and inches, pounds and ounces, gallons and pints. But with 12 inches in a foot, 16 ounces in a pound, and 8 pints in a gallon, and the rest, these imperial units were quite awkward to do calculations with. But across the English Channel, something exciting was happening. In 1789, there was a revolution in France that overthrew their government, executed their king, and took over power from the ruling classes, cutting off many heads in the process. The new revolutionary government wanted to change every aspect of French life, And one of those changes was to introduce a completely new and rational system of measurement, which would be based on something far more scientific than the length of someone's foot. So the French Academy of Sciences came up with the idea of a measure based on a 10 millionth part of the length of the arc around the Earth at sea level from the equator to the North Pole. That would be their new unit of length, and they would call it a metre, from the Greek word for measure. It took French surveyors and mathematicians several years to work out the exact length of this new metre, and when they had, an accurate metre bar was made in platinum and kept in the French National Archive as a permanent reference. Here's a copy of that standard metre bar in the Science Museum collection, made of brass. The French Academy came up with more units based on their new metre. The unit of volume would be a cube of sides exactly 1/10 of a metre, which would be 1 litre. And the mass of 1 litre of pure water would be 1 kilogram. What's more, all these new French metric units would have larger and smaller versions based, logically, on multiples of 10 to make it easier to convert between them. They were all given logical names. So 1 kilometre is 1,000 metres, 1 kilogram contains 1,000 of these tiny grams. There are 100 smaller centimetres in a metre, and 10 even smaller millimetres in a centimetre. In their revolutionary further, the French went even further, and in 1793 they proposed a system of metric time based on a 10-day week and a 10-hour day. But would this new rational system catch on? Well, not surprisingly, it wasn't too popular with the people of France. The new decimal calendar and the 10-hour clock was forgotten about after a few years, but the other metric measurements eventually began to catch on in Europe. It was only when Britain joined the European community in the 1970s that our old imperial feet and inches, pounds and ounces started to be replaced by European metres, litres and grams, though we still hang on to our miles and our pints. So where did algebra come from, with all those equations with their x's and y's? In fact, we didn't have x's and y's until about 300 years ago, but solving problems with unknown quantities has been around for thousands of years. In ancient times, what we call equations were word problems involving quantities such as length, weight or money. There's a famous Egyptian mathematical papyrus from about 1650 BC called the Rind Papyrus, and in it there's an example of an equation. It says, if a quantity plus a quarter of it equals 15, what is the quantity? We could write this problem as an equation. A quantity x plus a quarter of it, 1/4 x, equals 15. And then work our way through it to get x equals 12. The Egyptians had a different method. They'd guess. So let's guess that the unknown quantity is, say, 4. Plus a quarter of it, that's 1, making 5 altogether. That's 3 times too small, so let's make the unknown quantity 3 times bigger. That's 12, and try again. 12 plus a quarter of 12, that's another 3, equals 15. Correct. The trail takes us next to Persia, that's present-day Iran. The father of real algebra is the 9th century Persian mathematician Al-Khwarizmi. He wrote a book about solving problems with unknowns, and it was called The Compendious Book on Calculation by Completion and Balancing. The Arabic word for the completion is algebra, which is where we get the word algebra, and a lot of algebra is still about completing and balancing equations. In his book, Al-Khwarizmi was the first mathematician to set out some standard methods for finding an unknown quantity in an equation. He gave the example of what we'd write as x squared equals 40x minus 4x squared. Al-Khwarizmi explained how to get all the similar terms together, in this case by adding 4x squared to both sides of the equation, and how to simplify it by adding, subtracting, or dividing by the same quantity on each side of the equation to keep it in balance. In this case, dividing each side by 5x gives the answer x equals 8. Al-Khwarizmi's method is exactly the way we simplify and solve equations today. So, in this book, written over 1,000 years ago, Al-Khwarizmi laid out all the basic principles of solving equations that we use today. In the years that followed, Al-Khwarizmi's algebra came to Europe, but mathematicians still worked in words, like this problem from the 13th century Italian mathematician Fibonacci. The cube and 7 things less 5 squares is equal to the root of 6 more than the thing, with the thing being the unknown quantity he's looking for. Over time, mathematicians developed shorthand ways of writing out these problems. This is how Fibonacci's cube problem might have been written 200 years later, with m for minus and p for plus, a dotted line for equals, and CO, short for cosa, Italian for the unknown. But with each mathematician using their own shorthand, these equations weren't easy to understand. It wasn't until the 17th century when French mathematician Descartes came up with the idea of using letters from the end of the alphabet for unknown quantities that we finally got our familiar X, Y, and Z. Now that these symbols have become standard, algebra is a universal language of mathematics which can be shared around the world and everybody can understand it. Well, almost everybody. Maths developed in Europe based on ideas from India and the Arab world, but long before that, from around 600 BC, the ancient Greeks had a mathematics of their own. The ancient Greeks had a clumsy and confusing system of numbers which used all the letters of their alphabet and no zero, so they found calculations hard to do. The Greeks preferred to think of mathematics in terms of lengths, areas, volumes, and ratios, and would discuss it in words rather than write it down. They called their mathematics geometry, earth measure, and most of the geometry we do today comes from the ancient Greeks. Like many civilizations before them, the Greeks knew the importance of maths for trade, building, and navigation. But to them, maths was really a philosophy, a way of thinking, which was important to study in its own right. It wasn't enough for the Greeks to know that something was true. They wanted to know why it was true, and if it was always true. They wanted to prove things, and it's this idea of proof that was one of the most important mathematical ideas we got from the Greeks. One Greek mathematician whose name we all know is Pythagoras, who lived in the 5th century BC. We know about Pythagoras because of the famous theorem named after him about right-angled triangles. It says that the square on the side opposite the right angle equals the sum of the squares on the sides containing the right angle. Today, we write this as a squared plus b squared equals c squared. But the Greeks used actual words to describe actual squares sitting on the side of an actual right-angled triangle. Pythagoras wasn't the first to appreciate this special property of right-angled triangles. The ancient Egyptians used rope with knots in it, or wooden set squares with side lengths such as 3, 4, 5 or 5, 12, 13, which they knew from experience would give them a right angle. And this Babylonian clay tablet has a diagram of some right-angled triangles. But it was Pythagoras and his followers who proved that this theorem was true for any right-angled triangle. He considered 4 right-angled triangles that make a square and contain another square, and described how to move them about in various ways to prove it. There have been hundreds of other proofs since, but Pythagoras' theorem is still one of the most important, useful, and elegant in all mathematics. Another well-known Greek mathematician is Euclid. Around 300 years BC, he wrote, probably with others who worked with him, a remarkable series of 13 maths books called the Elements. They were written on papyrus scrolls, so there's nothing left of them. But Euclid's work has been copied and translated from one language to another, right up to the present day. Here's an English translation in 3 volumes, and here it is on the internet with interactive diagrams. There had been mathematics books before, but Euclid had a unique approach. He began with a few agreed definitions, like the ends of a line are called points, and some basic assumptions such as things which equal the same thing also equal one another, and then used them as the starting point for his proofs. In the Elements, Euclid covered all the mathematics that was known at the time, the fundamentals of geometry, the properties of triangles, circles, and 3D shapes, ratio and proportion. He started with geometrical constructions that can be done with a straight edge and a pair of compasses. And here's the first one, Book 1, Proposition 1, how to construct an equilateral triangle. Something we still do exactly as Euclid described. And when you're doing circle theorems and you notice that the angle at the circumference is always the same, you can turn to Euclid's Book 3, Proposition 21, and here it is. In a circle, the angles in the same segment equal one another, which he proved 24 centuries ago. In his Elements, Euclid's whole idea was to start from something simple, agreed and known, and then build on it logically step by step to prove something far more complicated. Thanks to Euclid, the idea of rigorous mathematical proof based on logical thinking was born, which is still the basis of modern mathematics.